Hi everyone, this is the first CNCM physics lecture. It is going to be part of a series for F equals MA and PHO Olympiad prep. And this first topic is circular motion and gravitation. So I'm going to start with the introduction to circular motion. Many of you might already know this, so if you do, then just skip ahead. So let's start. Tangential velocity is denoted by the letter V, and it is basically if a body is moving in a circular path. This is the body. Then v would be the tangential velocity. So the velocity of that path on the tangential in the tangential way, and it is denoted by meters per second. Next, you have angular velocity. So let's say a body traverses an angle of theta. This basically measures how fast it traverses that angle, and it is denoted by omega equals or is radians per second. The next quantity is tangential acceleration, which is just the rate of change of tangential velocity, and that's in meters per second squared. And the final quantity is angular acceleration, which is denoted by alpha, and the units are radians per second squared. Now, we're going to move on to this formula. So right here, 1. Frequency is basically how fast it can go through one revolution. So the time per every one revolution. Omega is how fast it can go through 2 pi angles. So how fast it can go through 360 degrees. So how fast it can make a full rotation. Alpha, which is angular acceleration, is just the change in the angular velocity divided by the change in time. Omega is change in angle, so how much angle it traversed divided by change in time. These two are very important formulas. So the angular acceleration is the acceleration tangential divided by the radius of the path's motion. The angular velocity is the velocity divided by the radius. And this one is actually going to come into play later. Finally, we have velocity is equal to 2 pi r over t, and this basically explains how velocity is total distance, which is 2 pi r, the circumference of the circle divided by time. So moving on to our first major topic in circular motion, which is centripetal force and acceleration. So centripetal force is a force that acts radially on a body moving in a curved path, meaning it acts in a way that is perpendicular to the tangent line. So in a uniform circular motion, a body has a constant speed and it travels in a circular path. These two must happen to have centripetal force. An example of this is the moon revolving around the Earth. The gravitational attraction between the Earth and the moon is balanced out by centripetal force. As you can see right here, I'm going to draw a diagram. So the gravitational attraction is going to pull the moon and the Earth together. And if these two are the only forces acting into play, then the Earth would have collided into the moon by now, and we would probably all be dead. But saving us all, we have centripetal force, which acts outwards on the moon in a circular path, which balances out the force of gravitational force, which we'll learn about later. Now, moving on to our centripetal formulas. So this first formula says that acceleration of centripetal force is equal to v squared over r. If we plug this into our F equals ma, into our a variable, we get the force of centripetal acceleration, or the force, centripetal force is equal to mass times v squared over r. I'm sorry about that. So if we want to convert this into angular quantities, instead of having tangential velocity, we want it to be in angular quantities. What we can do is we can simply rewrite this as m times v over r times v. And from our first slide, we can remember that omega is equal to v over r. So we can substitute this v over r into our f of c. So we have fc is equal to m omega v. This is still not what we need because we still have this velocity inside the function. So what we're going to do is we're going to multiply both sides by r, and we'll get r is equal to, multiply both sides of this equation by r, and we'll get r is equal to, we'll get v is equal to r omega. So now we can just substitute velocity into this function, and we'll get force of centripetal equals mass times omega times r omega. Rephrasing this or rewriting this, we'll get m omega squared r. And this is going to be important for the problem that we're about to do next. Okay, so moving on. So this is our first problem, acceleration of a revolving ball. A 0.15 kg ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.6. The ball makes 2 revolutions in 1 second. What is its centripetal acceleration? So we have a ball and it's moving in a circle. The radius of this ball is 0.6 and the mass is 0.150 kg. So we're missing here is a velocity term. So what we're going to do, or angular velocity or velocity, we need either of those. So it makes 2 revolutions in 1 second. So omega is equal to, the total angle traversed in 2 revolutions is 2 times 2 pi divided by, the ball does that in 1 second. So we get omega is equal to 4 pi. Now, coming back to our old formula, since it's asking for centripetal acceleration, we just do A of c equals omega squared r. So plugging this omega and our radius in, we will get centripetal acceleration is equal to 16 pi squared times 0.6. And if we were asked to find the force, which we're not, I'm just hypothetically, if we were asked to find the force, then we would just multiply the acceleration by the mass. So f of c would be 0.150 times 16 pi squared, running out of space here, times 0.6. So let's say we have a car making a turn in this scenario, and a 1,000 kg car is making a circular turn with radius 26 meters. If the force of friction on this car is 700 newtons, what is the maximum speed that the car can drive without flying off the road? So let's say the car is right here. Inside we have 700 newtons, and outside we have our centripetal force, obviously. So to find the maximum speed that this car can travel, we have to equate these two quantities. So mv squared over r is equal to 700. And if we rearrange this to solve for r, we'll get square root of 700 r divided by m. Once we plug this into our calculator, we'll get the velocity to be approximately 4.27 meters per second. Now, so this is basically saying that the velocity can be a maximum of 4.27 meters per second. And if it's more, then the centripetal acceleration will overtake and it will cause the car to drift off the side of the road. So now we're going to move on to a little more of an advanced topic. And for this topic, you'll have to have some prerequisite knowledge of vectors in component form and free body diagrams. And this topic is basically banking of roads. So sometimes in NASCAR driving, for example, the roads are banked so that the cars can enter at high speeds without having to worry about centripetal force that much. So these cars are banked as seen in this diagram, and there are several forces that are applied to it. So this is why we have to have a semi-good knowledge on free body diagrams. So I think this topic is best illustrated by a problem, so let's do one. Banking of roads. A car is driving at a speed of 10 meters per second around a curve of radius 52 meters. Find the minimum angle such that the car remains balanced on the curve. So we're trying to find the minimal angle that the centripetal force does not overtake. So let's draw this. We have a car right here, and it's driving at a velocity of 10 meters per second, and the radius of the curve is 52 meters. And we have an angle here, theta. So let's start and draw all the forces acting on this. So this is still theta, I just want to make it smaller. So first and foremost, we have mg acting down, the force of gravity. It's always acting down. And we have normal force, which is always acting perpendicular to the surface. So now we can't form any equations out of this, so we have to split this mg vector up into its components. And this splits up into mg cosine theta, and here we're going to have mg sine theta. And finally, we have all our forces except for centripetal force. So we're just going to add that right here, mv squared over r. So we want to find the minimal angle such that the car remains balanced on the curve. So we're going to have to equate mv squared over r is equal to mg sine theta. So the first thing I noticed when I wrote this equation is that the masses can cancel. And what we're going to try to do is isolate sine theta so that we can take the sine inverse and get the angle. So what we're going to get is sine theta is equal to v squared divided by rg, which is equal to, if we're going to plug this into our calculator, we'll get 0.196. We're not done yet. So what we're going to do is take the sine inverse of 0.196, and what we'll get from that is approximately 11 degrees, so 11.3 degrees. We are still not done with this problem because the standard unit for theta is not 11.3. We have to convert this to radians. So we'll get 11.3 over 1 times 2 pi over 360. And what we're going to get is, we will get 0.197 approximately. So this is going to be 0.197 radians. So now moving on to Newton's law of universal gravitation. And this is one of the most important laws in physics because it works all across the universe. It's not just restricted to Earth like some of the other laws. And so what it basically says is F is equal to G m1 m2 over r squared. So let's say we have two masses, m1 and m2. Every mass has a force of attraction between it. So this mass is attracted to this mass by force F, and that is equal to Gm1 m2 by r squared. Squared. So both masses are attracted to each other by this force F. And this is amazing because this is the basis of planetary motion. Planets are able to stay in their orbits by a balance of Newton's law of universal gravitation and centripetal acceleration. And these are some constants that you have to memorize to solve problems in this subject. So the mass of the Earth is 5.972 times 10 to the 24th kg. The radius of the Earth is 6.37 times 10 to the 6th. And the gravitational constant G. So moving on to our next problem. calculate the centripetal acceleration of Earth in its orbit around the Sun and the net force exerted on the Earth. Assume that the radius of the orbit is 1.5 times 10 to the 11th and the mass of the Sun is 2 times 10 to the 30th power. Okay, so we have the Earth, and here you have the Sun, and it is in its orbit. So it's orbiting around like this. The radius of the orbit is 1.5 times 10 to the 11th power, and the mass of the Sun is 2 times 10 to the 30th. Okay, so let's see. So let's draw a free body diagram on the Earth. So that's the Earth. We have mv squared over r acting this way, and we have gravitational force acting this way. So actually, let me rewrite this. So this should be mass of the Earth v squared over r, and this is equal to g times mass of the Sun times mass of the Earth over r squared. So let's equate these two forces. Or these two, yeah, let's equate these two. Okay. Equals mass of Earth times v squared over r. Mass of Earth and mass of Earth cancel. And what we have left is v squared over r, which is the centripetal acceleration. So we have v squared over r equals g times the mass of the Sun over r squared. So let's just calculate this portion, and we'll get our answer to that question. So g is 6.67 times 10 to the negative 11th times the mass of the Sun times 2 times 10 to the 30th, all divided by the radius squared. So 1.50 times 10 to the 11th squared. And we'll get a centripetal acceleration of 0.0059 meters per second squared. Alright, so let's do the next part of this problem, which is find the net force exerted on the Earth. Well, you see we have GMSME over r squared exerted this way, and we have ME v squared over r exerted this way. So we can just plug all of this in and subtract whichever one's higher, and we will get the net force. And you guys can try this one on your own time. I'm going to move on to the next one. So now we are going to do a problem in which we need to find gravitational acceleration on Earth. Let me go back. So the gravitational acceleration on Earth. So let's say we have our Earth here. And to find the gravitational acceleration, we take a mass and we put it here. And we want to see the acceleration and how much it's attracted to the center of Earth. So the force on the mass will be mg, which is equal to, I have it written up there. So mg is equal to g times the mass of the body times the mass of the Earth divided by the radius of the Earth squared. Instantly, I see that these two masses cancel. So g is equal to g is equal to capital G times the mass of the Earth divided by the radius of the Earth squared. So we're going to try this, and we will get G. We'll get G equals 6.67 times 10 to the negative 11th times 5.972 times 10 to the 24th. That's the mass of the Earth. And the radius of the Earth is like 6.37 times 10 to the 6th squared. And solving all this, we should get 9.8 because we know that 9.8 is the gravitational acceleration on Earth. So let's put this into my calculator just to check. and we do get 9.81 approximately meters per second squared. So you can do this on any planet. This isn't just restricted to Earth. So what we would do is the gravitational acceleration on any planet is equal to g times the mass of that planet divided by the radius of the planet squared. And this works for the moon, every planet. So our next topic is weightlessness, and I think this idea or topic is best explained by a problem. Well, actually, let me go ahead and give you guys some basic information. So let's say you're in a box and you have a spring scale and a person is standing on the spring scale. Well, that person's true weight, and let's say there's an arbitrary force W, and this is basically represents the weight of the spring scale. So your true weight, if nothing else is happening in the system, is going to be weight is equal to mg, and that's called your true weight. But if if the elevator is actually moving, then you might have a force of ma down. If the elevator is accelerating up, then you might have a force of ma going down, in which case your weight would actually be mg plus ma, which would be way heavier than usual. So let's look at this as an example. So what will a spring scale read for the weight of a 58 kg woman in an elevator that moves upward with constant acceleration 0.23 times g? So 0.23 times 9.8. So it's moving upwards. It's moving, so the acceleration is upwards. That means that the force of acceleration would be downwards. So this, in this case, weight would be mg plus ma. And we can factor out the mass here. And remember that it was 0.23 g. So we can add these two up and you get 1.23 g. And solving for this, you'll get 58 times 1.23 times 9.8, you'll get 699.132. So that's how much your weight will be if you are, if the elevator is moving upwards at an acceleration of 0.23 g. Now, let's do B, downward with constant speed 5 meters per second. So when you have a constant speed, that means that the acceleration is equal to 0. So if we do the same formula, weight is equal to mg plus ma, acceleration would be 0, and weight would just end up being mg. So if weight is mg, then, so let's solve the second part. Did this first. Weight is equal to mg. Then it's just equal to 58 times 9.8, and that is 568 newtons, 0.4 newtons. So when the elevator is accelerating, you feel 130.6 newtons heavier, which is quite a bit. So this final example is with the teeterball and fishing rod, and we see this kind of problem a lot in physics competitions. So while fishing, you get bored and start to swing a sinker weight around in a circle below you on a 0.25 meter piece of fishing line. The weight makes a complete circle every 0.75 seconds. What is the angle that the fishing line makes with the vertical? So feel free to pause it and work this out on your own, but I'm going to go ahead and start now. So we have this string, and here is our sinker weight. So if we have, this is the vertical, and that's theta. Or sorry, actually to make this easier, we're solving for this, but I'm going to make this theta, and then this is just 90 minus theta. So we have to subtract our angle by 90 at the end. So you get bored, let's see. So this is 0.25, and the weight makes a complete circle every 0.75 seconds. So it traverses an angle of 2 pi in 0.75 seconds, and that's going to be omega. And from this, we can see that omega would be 2 pi divided by 0.75 is 8.38. Yeah, 8.38 radians per second. So now what we're going to do is we're going to make a free body diagram with this sinker weight. So I'm going to draw it right here. You have T coming out, which is the tension of the fishing rod. You have mg going down because that's the gravitational force exerted on the ground. And you have mv squared over r because it's moving in a circular motion. So to make this easier, we can split this tension force into two separate vectors. So this is going to be T, I'll just write it up here. This one is going to be T sine theta coming up. So upwards you have T sine theta, and sideways you have T cosine theta. Alright, so from this we can make two equations. So T sine theta is equal to mg, and T cosine theta is equal to, what is it equal to? mv squared over r. So when you divide these two equations, so I'm going to try to get rid of the t. So I'm going to divide these two equations. So T sine theta divided by T cosine theta is just going to equal tangent theta equals mv squared over r. What we're going to get when we divide those two is gr over v squared, because the m's will cancel out. Now, v, from our first example from a long time ago in this lecture, we had omega is equal to v over r, and v is equal to r omega, right? So we can substitute that v back into this function. So tangent of theta is equal to g r over r squared omega squared. One of these canceled, so all you'll have is g over r. So tangent theta is equal to g over r omega squared. So we plug this in and take the tangent inverse of this. We'll get theta is equal to, let me do this on my calculator, divided by radius 0.25 divided by 8.38 squared. So, and tangent inverse of answer. We get 29 degrees for theta, but remember, we're solving for tangent, we're solving for this, 90 minus theta. So we're going to do 90 minus theta, which is 60.83. So our final answer is 60.83 degrees. Yeah, and this is a very common question, so you'll see this a lot if you decide to continue with competitive physics competitions. The end. So this is the end of the lecture. There's a PDF in the description of challenge problems from various sources. These are a little harder, and there's some basic level problems, but the majority of these are harder than what we've covered in the lecture. You can try to attempt these problems and DM your answers to me on Discord. If you're having trouble with any of them, please just send me a personal message. I'll be happy to respond. And as usual, don't forget to join our Discord. Link will be in description, and please subscribe. Bye.